When you hear the word levitation, you probably picture the hoverboards from Back to the Future, or magic tricks like this, but gravity-defying technology isn't just the stuff of science fiction, it's very real.
Acoustic levitation uses sound waves to counteract gravity.
Acoustic levitation is unique because, unlike magnetic levitation for example, it can effectively suspend both liquids and solids. But there's a small catch.
The largest object we've levitated has just been a 3mm bead.
But even at that scale, there are some exciting applications, like analyzing chemical reactions in suspension, the creation of better drugs, and even improved robotic arms that can manipulate tiny, delicate objects.
And you can trap an object to counteract gravity by creating a space where there's no force.
That's Chris Benmore, a physicist with Argonne National Laboratory who uses this gravity-defying technology. We spoke to him to find out how acoustic levitation works and what exactly it's used for.
Walk us through what acoustic levitation is and how it works.
Acoustic levitation uses sound waves to generate a force to counteract gravity. It was developed primarily by NASA in the 60s and the 70s to do ground-based experiments on looking at the effects of anti-gravity on Earth.
And can you walk us through the different components of the device that you have there and how the sound waves actually come together to produce the levitation?
These transducers basically drive these horns, the silver part. And so this horn will vibrate at 22,000 times a second up and down to generate a sound wave. And we have a match transducer down here and horn, and that will generate another sound wave. And when these two waves interact, you'll get what's called a standing wave. So they'll cancel in places and they'll reinforce in others to create nodes and antinodes. And those particular places where they cancel, you can put an object in and you can levitate.
All right, well, let's see this in action if you wouldn't mind giving us a demo.
Right now, I've created a standing wave. These horns, which I'm not going to touch, are vibrating at 22,000 times a second, creating a standing wave. And so I can put an object in that little cavity where the two standing waves cancel. In fact, there are several cavities where I can put objects. And so if I just have this brass rod here, you can see I can go through them. If I come in from the side with my hand, you see I get some reflections, I will disturb it more. So I will interfere.
Is there anything particularly special about the sound waves themselves, or is it more the way they're interacting that is really essential for producing the effect?
It is the way they're interacting and the particular frequency. So both of these devices operate at 22 kilohertz, and so that's just on the edge of human hearing. So you might hear it come in and out, okay, especially if I turn it up to the higher power.
Although it's loud, the sound waves are at such a high frequency, it's almost imperceptible for humans. You might just be able to make out a high-pitched pulse.
At that frequency, there is a spacing between the nodes of 6 millimeters. Okay, so this standing wave that's created will create pockets, and this 6 millimeter spacing limits you to how much you can put in there. So you can put an object in, so maybe half of that size, so something like 3 millimeters.
When you add a little object, how do you know exactly where to place it to get it in that right spot?
You can, of course, actually do the math and calculate it this is actually a very precise distance between the two. When you actually spray a mist of water, you'll get a vortex, and the droplets will be drawn to the most stable places within this region.
And when you place them, they almost look like they kind of snap into position. Is that the case?
That's exactly the case, yeah. So the standing wave is fixed by the geometry, and so they're every 6 millimeters. Okay, so if I try and put it close there, it will naturally lock into position.
And can we elaborate a bit on the limitations for size? Why are you limited to smaller objects? Why can't you, for instance, levitate me if I would want such a thing?
This is actually generating an awful lot of sound. Even though it's a pretty small device, it has about the same level of sound as a rock concert. So you could build bigger transducers and levitate larger objects, but it would be deafening for one, and also very destructive for another. You can imagine if you 10 times a rock concert to levitate an object that's maybe a centimeter in size. So you can imagine if you want to levitate you would have to build something enormous.
So given that you're working with focused sound waves, would it be possible for actually an outside actor, if they wanted to mess with your experiment, to throw their own sound waves at the device to disrupt the object that you're manipulating?
They certainly could, particularly on this device, because this is just a single axis levitator. So it really only counteracts gravity. It's pretty unstable in the horizontal direction. So quite often what people can do is have another levitator, say at 90 degrees to that, to stabilize it.
I think one of the other interesting things about the kinds of objects that you can put in these levitators is you can do solids and, as you had mentioned, liquids. Why would that make this particularly useful as a technology?
For us, it's an ideal device for holding a droplet in space with no other interactions around it, so you can just study that droplet.
Ben Moore and his team are currently using this device to analyze pharmaceutical drugs with the help of an extremely powerful X-ray.
We have the most intense X-ray source in the Western Hemisphere here at Argonne. And so what we're able to do is look at the atomic structure where all the atoms are arranged, and so we identify the molecular shape and how the molecules interact. So what it allows us to do is kind of trap that drug in that manufacturing process and give an idea of what conditions you need to actually make a more effective pharmaceutical.
At the present moment, you are levitating fairly small objects. Can you walk us through what it will take to actually scale that up to levitate bigger and bigger things?
But what people are trying to do now, and have successfully done to a certain extent, is to make arrays of these. So if you have a whole array of these, say you have 5 in a row in one direction and 5 in another, so you have 25, you can levitate a larger object just by levitating in certain places. Rather than having a bigger transducer, you just have more of them. And in fact, what they're able to do as well is to actually move objects around, because you can change the amplitude using software to vary the power in one transducer compared to another, so you'll be able to move the object laterally as well as vertically.
For example, take a look at this robotic arm that uses acoustic levitation to move objects without ever touching them, reducing the risk of damage or contamination. In the future, this could give robots a more delicate touch.
So this isn't the only form of levitation out there. Can you walk us through perhaps some other methods of actually levitating objects, and maybe why this is a more effective method in certain ways?
There are many types of levitation, from magnetic, electromagnetic to aerodynamic levitation. And in fact, one we use quite a lot is aerodynamic levitation, and this is really quite an easy one. If you've ever had a ping pong ball on a hairdryer, you can imagine how that one works. That is very effective.
Magnetic levitation, or maglev, can suspend something as massive as a train by using opposing magnetic forces. But acoustic levitation is unique because it's ideal for handling tiny, fragile objects and non-conductive substances like liquids.
This is soft enough that it will keep the droplet together. And of course, a lot of these droplets aren't magnetic, so we can't use magnetic levitation.
And looking forward, in the future, might we be able to speculate on other applications for this technology?
One application that's going on right now is a combining of an acoustic levitator with an aerodynamic levitator. So you can get the benefits of both.
And I have to ask, could you potentially make something like a hoverboard out of this technology, or are you inherently limited to the lab because you have to have these two devices interacting with each other?
You can actually make these devices very small now, and you can have many of them. So maybe not more powerful, but you could have a lot of them. I don't think it's enough to levitate a hoverboard, let alone a person, but you can certainly think about levitating heavier objects.
Thank you for blowing our minds today.
Well, thank you.